Good morning. Is there anybody who does not speak Czech?
Yes, hello.
Well, good morning. Then this lecture would be in English. So let's start. We have last been talking about finite difference time domain, and we had the first equations for that. So in fact, we know how to step in time, and we know that we begin from the situation when there is no electromagnetic field, because that's the situation we know exactly. I mean, 0 is an exact number. So now we have to proceed somehow to a situation when there is an electromagnetic field, because that's why we are doing that. So let us start with a simple example. One of those examples could be, for example, a class of tasks like find out a resonant frequency of a cavity. So find out a resonant frequency of a cavity. We have some cavity and we would like to know the resonant frequency. Now, how to do that? Well, first we have a cavity. Well, I'm now drawing an orthogonal cavity in 2 dimensions, but let's say it's an arbitrary shaped cavity. For this we have an analytic solution, but what if we forgot that solution and we want to find the frequency? So first we have to mesh that. So we mesh that by a set of orthogonal lines, and we set up the mesh for electric and magnetic field, and we put 0 into all those mesh values. That's the beginning. Now we have somehow to feed the structure by something that would result in finding the oscillation frequency and field behavior. Now, how to do that? We have, fortunately, one important source that would feed all possible frequencies in. Just remember, when you have been talking mathematics, then there was the Riemann integral, and then you possibly proceeded to some more complex integrals that have been integrating a unity pulse, or a pulse, a direct pulse, which is infinite in energy, or has energy in an infinitely short period. And this pulse has a spectrum that contains all frequencies, and in fact all frequencies in the same manner. So we have a pulse. If we feed the structure by a pulse, then we would get a response of the structure at all frequencies at which the structure is able to respond. Well, that was the mathematic background, but what shall we really do? Well, we have the structure, and suddenly we put into one place a value which is distinct from 0. So, and just once, so we start the calculation with a grid which has zeros everywhere, but in one point we insert a value. And now we start to leave the grid time marching on. So if we feed one point, then in the next step the pulse would propagate to the neighbors, and the next step to the neighbors of the neighbors. And we would have to proceed with time stepping for quite a long time, because in fact at the beginning we would have the same situation like an open space and a pulse propagating from one point. So it would be a ball in 3D or a circle in 2D that would be expanding from the origin. Now this would have inside no information about the boundaries, about the walls of the resonator. So we would have to wait till the energy reflects from the walls, and we would have to wait so long that the energy propagates to one wall, to the second wall and back. We would have to wait a lot of time. So a number of steps. Now, how to find out a resonant frequency? Well, I have told that we would have to wait for a number of steps. If we have 1 million points inside, even with today's computers, it would not be very nice to store all the values in each time step. You would run out of memory with 1 million steps, which each has 1 million points, very easily. So what about, for example, getting one other point as our output point and getting just one field value per step? So we have 1 million points inside, but we only record one value in each time. And now, if we run this simulation, we would get something like, so let's have the time x. This is the feeding, which would be green. We would have the output, which is red. And now at some time we insert a step, and that's all for the feeding. We would not feed it anymore. And now we would wait, and from that point, after some time, the information, if this is not just the neighbor, would propagate to the other point. So after some time we would start to have a response. And it would be more or less chaotic in time. But what we can do is, in fact, what we will get here is the reverbs from the walls. So we would have a set of chaotic pulses over here. But we can get this response and make a Fourier transform of that. At the beginning it would also look chaotic, but after some time, after some number of steps, you would see there some peaks. Now this is the Fourier transform. So this is frequency, and this is the Fourier transform, for example, of the electric field. So I would mark it somehow like this. Is the transform value into frequency domain. So you would find out a number of peaks. You even can find out the number of iterations necessary to get result. Just this would stabilize, and after some time you would get a set of peaks at frequencies which are the resonant frequencies of the cavity. So this is the way we can find out the resonant frequencies of the cavity. Now, normally, mostly a Fourier transform is pre-programmed or is done by a discrete Fourier transform, and that more or less means that the programming is much simpler if the number of time steps is a power of 2. So you would possibly run the calculation for 1000 or 1024 or similar numbers, 2048 samples, and you would only make the Fourier transform at those powers of 2, because that's simpler. And once you get a stabilized picture, you know that you have found the resonant frequencies. Seems simple, but there is a problem in it. Just the important point, let's again investigate a rectangular cavity. So the first, well, let's have a long cavity. One dimension is much bigger than the others. Then a rectangular cavity would have inside the dominant mode of a rectangular waveguide. So the behavior of the field would be, at least to the electric field, that would be a half sine wave in the width, So we would have a half sine behavior in this direction, and the first mode would be TE101. That is, there would be no halfway in this short dimension, one halfway in the longer dimension of the cross section, and one halfway over the length. So that would be something like this. And this is simple. And if I feed, for example, the cavity over here, and I read the data over here, I would get this mode. What is the next mode of this structure? Well, I will draw it in green. This structure has a second mode, more or less twice the frequency of the original one, and that would have two half waves along the largest dimension. It would be the TE102. And that is a problem, because this something has this field behavior. The same behavior in the cross section, but a different behavior in the length. And if I just fed the structure in the middle, in fact, I will give no feeding to this mode. So even if I have fed in the frequency that would result in this oscillation, I did not feed it in proper place. And then you would have another mode which would have three half waves. And this is the second mode I will find out here. Why am I telling that? Well, if you have one feeding point and one observation point, you will find a number of resonant frequencies. And yes, any of those frequencies is a true resonant frequency of the cavity. But there might be other frequencies that you oversee in this manner. And that might be due to two facts. First, you could never observe resonant frequencies which have zero field in the point of observation. And you can never invoke resonances in the structure if your feeding point has a zero field at that resonant mode. So practically you would miss some modes if you have wrong observation and wrong feeding points. Now, for a waveguide or a rectangular cavity, this would be simple. You know where the zeros are, so you would put good feeding points. For example, a good idea is to set up several feeding points. My personal guess is 3, and those are randomly placed in the cavity. And you have at least 3 observation points, which are also randomly placed in the cavity, so that you have a good chance that you invoke all the modes and you at the same time observe all the modes. Again, the other solution would be for feeding the structure to start with some field at any point, so that you would not oversee any field, any mode. You would invoke the mode, and to observe it, you would have to observe at all nodes, but that would require in storing all the values along the numerical simulation, and that's rather much value. First for storing and second for elaboration. You would not be able to calculate the Fourier transform for all the nodes in the structure in a finite time. So that is the way how you can use finite difference time domain method in order to find out the situation in a cavity. And the cavity we have shown was a rectangular cross section, because I could easily show you the modes and tell you why this way of sampling does not work at some time. But on the other hand, this is more useful for arbitrary cross-section cavities which have no analytic solution. So we do not know the field behavior, and we have to use the numeric method. The second question would be, well, okay, I know the resonant frequency. How to find out the electromagnetic field in the cavity? And now, once you know the frequency, you can switch your strategy and say, okay, I will find out the electromagnetic field just at this frequency. Okay, I would then feed the structure by a single frequency. So instead of putting that there just one non-zero value, I would force this value to obey a sign dependence on time with the frequency that belongs to the resonant frequency. And then I would get only one frequency in the cavity. I would have a pure harmonic feed-in signal. And that would result in only one mode, which is in the cavity. Again, there is the story. I have to feed it at a point when the field of that mode is non-zero. But in fact, if I have detected it, I must have been feeding the structure at a point where the mode has a non-zero field. So if I do not move the point, I can't make a mistake. Now, this was the simplest possible task we could solve by a finite difference time domain method. We did not need to know quantities. In fact, our results were relative, resonant, non-resonant at that frequency, and the shape of the field distribution. So we were not taking care about quantities like transmission or reflection. We have been just taking care about resonant frequency. Is there resonance? Is not there resonance at that frequency? And as the second point, a shape. But we only required relative numbers at the point. Now your questions, please. Well, I can't see any questions at the moment, and so I will proceed a little bit on. Now we will have an important question or an important mechanism I have to show you, which makes trouble with our method of field time evolution. And that, if you remember, I said with the leapfrog algorithm, we have a nice algorithm which is based on the knowledge of the half-step future value. And this algorithm is very effective and is conditionally stable. And this conditional stability requires that the time step does not exceed a certain value. Now, there is a physical, let's say, a physical insight into the method that tells you why. Just imagine you have a real problem. So, a real problem where the information is propagating with the velocity of light, c, 300,000 kilometers per second in free space, for example. Now, you cut it into a grid. Let's use a 1D problem at the moment. So you have some lines that are delta x distant one from the other. And you have some time step, which would be delta t. And now in reality, in continuous case, the signal propagates with the velocity of light. Now, in our discrete case, this is not fully the situation. In fact, you would have the maximum propagation with our approach that gives you shifting the waveform one cut in one time step. You remember, there is no dependence of the values over here on the values that are two discretization steps far. There is only a dependence on the neighbors. And then the maximum shift would be one step. Now, if you have the time step set up so that the propagation velocity in the media times the time step is the discretization step, talking about 1D, we just get the signal from here to here in one time step. And that's fine. I mean, the model is capable of moving the waveform one discretization cut forward in one time step, and the reality does the same. Now, if you increase the time step, in fact, the real situation would be that the waveform moves more ahead than it could in the discretized case. And in this case, you would get a wrong result, which would, in the differential equation situation, turn out into instability. So you would get possibly more and more field values increasing, and after some amount of time steps you get an overflow in your computer. So you can never increase this. So then you would have to obey this rule